Since we started studying the firm, we've made the assumption that firms are looking to maximize profit. So a firm would like to choose the quantity of output, Q, that maximizes their profit, pi of Q. What is pi of Q? Pi of Q, their profit, when they produce Q units, is the revenue that they get when they produce Q units, minus the cost of producing Q units. Remember, the expression here is the economic profit. This is not the same as the accounting profit, because C of Q is going to include opportunity cost as well, not just the accounting cost or the explicit cost. We're looking at competitive firms here. In Micro 2, you'll look at non-competitive firms, so monopolies and oligopolies and so forth. The revenue function for a monopoly, for example, is going to be different. But since we're looking at competitive firms, the revenue when you sell Q units is simply the price times the quantity that you sell. So your profit is quite simply P times the quantity you sell minus the cost of producing Q units. Now there's two steps to maximizing your profit. The first is, if you're going to produce, what's the optimal quantity to produce? You need to figure that out. We'll call it Q star. So what is the quantity Q star that gives you the highest level of profit? Second, if you did produce that optimal quantity, is your profit going to be positive? Or are you going to make a profit? Or should you just shut down? By shutting down, I mean, should you just set Q equal to 0? So let's look at what it means to pick the optimal level Q star, and then we can talk more about the second part, where you decide whether you should shut down or not. The shape of the profit function is typically going to look something like this. Given certain assumptions that we're going to make on the cost function, the profit function is going to be a concave function. So in order to find the optimal Q star, this looks like a familiar exercise to you. You find the part of this little hill where it's flat. That means you look for the point where this profit function has a 0 derivative. So you want to find the Q star where the profit function has 0 derivative. So the first order condition is to set the derivative of profit to 0 and solve for Q. But remember, this first order condition only gives you a local maximum. It could very well be that this maximum is still negative. So you might have had a picture that looked like this. So this is your profit, that's 0, that's Q, and it could very well be that your profit function looks like that. So when you find the optimum Q, it's going to be, Q star is going to be here, but your optimal profit is actually going to be, so your profit at Q star, which we'll denote by pi star, is going to be negative, which means that you're making a loss in the best of scenarios. So even at the best Q quantity that you could possibly pick, Q star, you're still making a loss. So the best thing for you to do would be to pick quantity 0 and shut down. For the moment though, we won't worry about this, and we'll come back to that in a little while. So we'll focus on the first order condition and worry about the shutdown rules later. So let's look at that first order condition. Remember, the profit function is just the revenue minus cost. The derivative of the profit function is the marginal profit. So it's the extra profit you get from a tiny bit more of output. This consists of two parts. If we take the derivative of pi, it's the derivative of r minus the derivative of c. And the first order condition says that that has to be equal to 0. dr dq is the marginal revenue. This is the extra revenue you get from selling one extra unit of output. dc dq, well, that's just your marginal cost. So if we define your marginal revenue as being the derivative of your revenue function, and your marginal cost we've already defined as the derivative of your cost function, The first order condition amounts to saying that at the optimal Q star, marginal cost and marginal revenue have to be equal to one another. So if you are going to be producing some quantity Q star that's not zero, then you should be producing a quantity where the marginal revenue is exactly equal to the marginal cost. I've set this up in a sort of abstract way without pinning down exactly what marginal revenue is, because that'll be helpful to you in future courses. So when you go to Micro 2, for example, the marginal revenue is not going to be very simple like it is in the competitive setting. In the perfectly competitive setting, on the other hand, the marginal revenue is very, very simple. If you sell one more unit, you're just going to get P more dollars. That's because the firm's residual demand is a horizontal line, and so they can sell as much as they want at the price P and nothing at any higher price. So what's the revenue and what's the marginal revenue? Well, the revenue is just P times Q, like we saw earlier, and the marginal revenue is just a derivative of this with respect to Q, which is just P. So the marginal revenue for for a perfectly competitive firm is very simple. It's just a constant. So for every unit you sell, you get P dollars. So for the extra unit you sell, you also get P dollars. So the marginal cost is typically going to be an increasing function of Q. So that's the assumption we're going to make in order for the profit function to be concave. If you make that assumption, to find the optimal Q star, notice this guy is increasing. So that's an increasing function. P is a constant, so it's going to be a horizontal line at P. So if you write down the marginal revenue. So if you want to find the point Q star where marginal revenue equals marginal cost, you just have to set marginal cost exactly equal to P. And that'll give you the Q star that is optimal for maximizing profit. Of course, it's important to remember that you need to check the second order condition whenever you solve an optimization problem. The first order condition says that you set the first derivative of the profit to zero, and that's only going to guarantee that Q star is maximizing the profit when the profit function is concave. Right? So if you had some function that looks like this and you look for the part where the derivative is zero, so the flat part, setting the derivative equal to zero gives you the optimum. But what if you had a convex function? Well, setting the derivative equal to zero actually gives you the bottom. So if you're going to use a first order condition to find the optimum, then you need to make sure that what you're optimizing is indeed concave. How do you know that a function is concave? Well, you take the second derivative, and that second derivative needs to be negative. So that's the second order condition. Remember that the derivative of the profit function is marginal revenue minus marginal cost. So if I take the second derivative of the profit function, I get the difference between the derivative of the marginal revenue and the derivative of the marginal cost. So if this thing is negative, that means that the first term has to be smaller than the second term. So the derivative of marginal revenue with respect to quantity has to be less than the derivative of the marginal cost with respect to quantity. So the marginal revenue curve has to be flatter than the marginal cost curve. Remember, the marginal revenue curve here is just a flat line for the competitive market. Of course, you're going to see in Micro 2 that the marginal revenue is going to be more complex. But for the competitive market, the marginal revenue curve is a flat line. So as long as the marginal cost is increasing, this condition is going to be satisfied.